Hello, this is Marvin Ray Burns. Now here I am. Hi. Uh, I've been a little negligent in describing the MRB constant thoroughly or clearly. So I'm going to start out this progress report with a thorough definition of the MRB constant. I'm going to use Math World as an outline and basically describe everything that they say. Okay, let's put my picture back, beautiful picture back on there. Move myself out of the way. Okay, the MRB constant. Let's see here. I'm going to get this where you can see it and me. There we go. Okay. When I started describing the MRB constant, all I really knew was high school level math. I knew about roots of numbers like square root, cube root, fourth root, fifth root. And see, I heard that there were people breaking records for computing the pi or e or the square root of 2, for instance. And that got me thinking, what about other roots like the cube root of 3 or the fourth root of 4 or the fifth root of 5 or the sixth root of 6? Just k to the 1 over k just appealed to me for some reason. So I started computing digits of the square root of 2, the cube root of 3, the fourth root of 4, the fifth root of 5, and so on. Got lots of digits. And then I wondered, well, that's a lot of constants. Uh, really, how would I pick one to really concentrate on and do something with? So I decided to add them together. When I added them together, uh, 1 plus the square root of 2 plus the cube root of 3 plus the fourth root of 4 plus the fifth root of 5, I found out that that diverged to infinity. That didn't help me much. So I heard about alternating series. So I decided to add them up in the alternating series. And when I did, I got a sequence of partial sums. Here we see S sub n, right here where it's highlighted blue. S sub n equals the sum of negative 1 to the k times k to the 1 over k from k equals 1 to n. So what that's doing is what I did at the beginning. I started summing negative 1 plus the square root of 2 minus the cube root of 3. And when I sum negative 1, which is negative 1, I noticed that that was the first S sub n, negative 1. So on this plot here, it's a little hard to see, but there's a spot at the bottom left-hand corner where the y-axis says negative 1. And if you look at the first graph line going almost straight up but not quite, you see it starts at negative 1. Okay, so then there was another S of n. That was negative 1 plus the square root of 2. Well, the square root of 2 is about 1.4 something. So negative 1 plus 1.41 is 0.41. That's where that save word was. This graph might be a little misleading. It goes just barely past the 0.4. It looks like it should go just a smidget more, but I guess that's how graphics are when you copy them on the internet and post them. And they, well, first of all, they go from the software to your editing page, and then they have to go to the internet. So it's probably a little hard to see the very top of that, but that should be 0.41. So we had -1, we had -1 plus the square root of 2, and then I had -1 plus the square root of 2 minus the cube root of 3. And that's a little less than 1. You notice go across the -1, a little less than -1, I should have said. You go across the -1, and you see the second graph line almost straight up and down. It's a little less than -1. That's -1 plus the square root of 2 minus the cube root of 3. And so the person who wrote this article, his name is right here. Eric W. Wistine, if I pronounced that right, but there it is spelled out. He plotted these partial sums in Mathematica from the first one up to, let's see, 100, up to -1 plus the -1 plus the square root of 2 minus the cube root of 3 plus the fourth root of 4 minus the fifth root of 5 plus the sixth root of 6, all the way up to 100 plus 100 to the power of 1 over 100, which I think it's the upper limit. You look at the last almost straight up and down line in the graph that passes through 100. You look at the top of it, and it's a little over 0.2. It really converged pretty slowly. Those even numbers converged. You see the odd numbers converged to the odd. I call it the odd limits converged to a certain number, and the even limits converged to a certain number, or toward a certain number, I should say. They didn't quite get to where they're going to stop, but the even ones, or top ones, went from 0.4, right over 0.4, to a little over 0.2. And it goes down a little more than that eventually. So he said, as can be seen in the plot above, the sequence has two limit points, -0.8, 12140, and 0.187859, which are separated by exactly 1. Okay, they're separated by exactly 1 once you get to infinity to the power of 1 over infinity. And the point on the graph right before that, point on the x-axis right before that, whatever that is. The one before infinity, the 1 over infinity, is -0.812140, and the one at infinity is 0.187859. It's kind of awkward saying that. I probably ought to cringe. Probably I have some mathematicians cringing at me saying it that way, infinity point. How do I know if infinity is odd or even? I don't know. I was just assuming it was even, but it's probably neither. But at that place, wherever it is, however you describe it, the two limit points are separated by exactly 1. That is because the limit of k to the 1 over k as k goes to infinity is exactly 1. You can figure that out on your own. The upper limit is sometimes known as my MRB constant, after my initials. I wrote Simon Plouffe about that in 1999, and he published it. The links are kind of hard to come by, and lots of them are out of date. You can eventually find one that works, though. At least I have found one that works, where I wrote him in my ignorance about math and ignorance about writing. But I wrote him anyway and said, "Look what I found." And he said, "Well, okay." And I'll put it down in my table of constants and see if anyone else has any interest in it over the years. And sure enough, a few people have. A few mathematicians have. And that's really made me proud. Okay. Now, the MRB constant can be found various other ways through various methods of summing. The one we talked about was this first one, where it's blue right now. The limit as n goes to infinity of -1 to the power of n times n to the 1 over n, where n goes from 1 to 2 capital N. And that's the limit as capital N goes to infinity. So in other words, going back up to our graph, that's a point I tried to describe on the top right. That would be on the top right corner if n went to infinity. Okay. Now, since the limit of n to the 1 over n as n goes to infinity is 1, as I tried to describe before, the limit as capital N goes to infinity of -1 to the power of n times n to the 1 over n from n equals 1 to 2 times capital N plus 1 is 1 1 less than the limit that goes to 2n. Or as he says here, the limit S equals the limit of the sum that goes to 2n equals 1 plus the limit as n goes to 2 capital N plus 1. Now, so what we have here is 1, -1, minus the cube root of 3, minus the 5th root of 5, minus the 7th root of 7, and so on, with all those odd terms. Terms involving those odd integers. And we also had 2 plus 4 plus 6, 2 to the power of 1 over 2 plus 4 to the power of 1 over 4. By the way, 4 to the 1 over 4 is the same thing as 2 to the 1 over 2. But I regress. Plus 6 to the power of 1 over 6 plus 8 to the power of 1 over 8. And that's what he has here in this third line. S of n equals the first one, equals this 1 plus this 1 on the second line, equals the sum of these even n to the power of 1 over even n minus the odd n to the power of 1 over the odd n, or equals the sum of 2k to the power of 1 over 2k minus 2k minus 1 to the power of 2k 1 over 2k minus 1 as k goes to 1 to infinity. And when you want to see a convergent series, which is good, we've been talking about divergent series until now, but the MRB constant is a convergent series. This 1, 2, 3, fourth line is a convergent series. It's let's see, it's convergent. Um, it's not absolutely convergent, but it's convergent. We'll see an absolutely convergent series involving the memory constant in a little bit. But you find out that if you subtract 1 from each term, if you subtract 1 from 1, plus the square root of 2 minus 1, minus the cube root of 3 minus 1, plus the fourth root of 4 minus 1, and keep going. If you sum those up from 1 to infinity, you get an absolute you get a not absolute convergent, a convergent, you get convergence to the MRB constant, 0.1878596424, etc., etc. Um, it wasn't long after I discovered the MRB constant, or first described it. Some people kind of get carried away or get upset when I say I discovered something. Um, I don't know if it's that important where I ought to brag about being a discovery or a great discovery, but I discovered it. That's how I feel. But when I first described the MRB constant, not long after I first described the MRB constant, I wrote um, the online encyclopedia of integer sequences, Neil Sloan's website, and he put it in there as A037077. A quick look at it. Right there it is. Decimal expansion of that limit. Actually, in the comments, you see the series sum n from 1 to infinity of -1 to the n times n to the 1 over n diverges, oscillates, with the upper limit given by this sequence and the lower limit given by the upper limit minus 1. That's what I tried to say in the previous. So if you look up MRB constant this on a search engine, this will be one of the links. Or just remember A037077. So besides zeros and A's, you got 3777 in there. And when you search that, you'll find search OEIS, and A037077, and you'll see what's written there. It's been added on to through the years by other people as well as myself. Now, here, Eric, the author of this webpage, which is called Math World, by the way. You see the address right here. He says the constant can also be given as a sum over derivatives of the, if I pronounce that right, Dirichlet eta function. I'm sure I did not pronounce that correctly. Eta sub n as S equals, above we had S equals, well, the same S equals the sum, sum of the alternating series of the kth derivative of eta of k from k equals 1 to infinity, the negative of that. That was discovered by the late Richard Crandall, a chief scientist and Apple chief cryptographer. I'm not sure what that has to do with cryptography, but somehow he got interested in it. And I'm happy he did, because he found out that new identity, which is an absolutely convergent series. That is the absolute convergent series for the MRB constant. You see, if you take the negative 1 to the power k away from that, or you probably don't see it right now, but if you work on it, it converges without the negative 1. Without the negative 1, I think it is zeta, the kth. Well, I'm not sure. I'm not going to say that. But if you had negative 1 divided by k factorial times eta sub k, and took away the negative 1, that would be eta sub k over k factorial. Not eta sub k, it'd be zeta of k over k factorial, because eta is the alternating zeta function. A little confusing and hard to understand if you don't know the math. And if you do know the math and I butchered it, forgive me. The reader will just have to study it for himself a little bit and look for what I said and see what truth is in it. Here's another sum the late Richard Crandall discovered. Instead of taking the kth derivative of eta of k divided by k factorial, you take the kth derivative of eta sub 0 times c sub k, where c sub k is the c sub k is the partial sum of this series right here. And here it says eta denotes the kth derivative, or eta with eta sub k, eta raised to the, or eta, the kth derivative of eta sub x denotes the kth derivative of eta sub x, eta of x, evaluated at x. There's a reference to Crandall's paper here. I'll show you the link in a minute. No closed form is known for this constant. As Stephen Finch wrote when he was writing about the MRB constant in his book Mathematical Constants, page 450. Stephen Finch was another person I bragged to about. I discovered a new constant. I'm discovering a new constant. Look at it. Look what it does. And he published it in his book. I mentioned the Pluff link. I think this one does not work. Let's look at it. Yeah, this one does not work, but you can find it if you search hard enough on the internet. There was the Sloan integer sequence link, and I mentioned Stephen Finch Mathematical Constants, Cambridge, England, Cambridge University Press, page 450, published in 2003. He has a new book, Mathematical Constants 2, that just came out this year. Here's the Crandall paper. Crandall in a book, Crandall find in a book called Algorithmic Reflection Selected Works, PSI Press, pages 28 and 29, 2012. Late 2012, I think that's what that means. It says 2012B. And here's the Crandall paper that he published, United Algorithms for Polylogarithms, series and zeta variance, 2012A, the beginning of 2012, I believe that's what it means. After he died, I took the liberty of publishing that paper on my website. So if you look at marvinrayburns.com, pause the video and write down this address, and you can find it. You can search for it by probably entering marvinrayburns.com and add um, unified algorithms. That should find it for you. Or just, like I said, pause the video and copy that address I showed you. Um, the author here was kind enough to include my bragging about how many digits I computed of the MRB constant, and gave a reference to me, Burns MR, try to beat these MRB constant records on community Wolfram, the Wolfram community post. Let's see how many visitors I've had so far. Sometimes the link don't work for me. There it is. I think that link works better on other computers than mine because that's on my profile. Um, Sometimes I think it thinks I'm trying to edit and look at it at the same time. But I could be wrong about why it doesn't work sometimes on my computer. Hopefully it works on your computer better. To find this, you just search, try to beat these MRB constant records, and it usually will be the first link you see. And look how many visitors I've had so far on it. 80,261 visitors. I think that's a lot of visitors. I'm really proud of that. And the top is the unpublished note I sent to Pluff, an alternating series involving the nth root of n's, 1999. I sent it to Simon Pluff, and he's probably referring to the one I sent to Stephen Finch in 1999. I wrote everyone I thought would be interested. So that is the MRB constant. So we're going to look quickly now at the progress. Presently, just highlight this. Oh well, I'm highlighting a bunch more than I need. My mouse don't work. There's 790,528 iterations that have been done in 8.309 times 10 to the 5th seconds. It should take 64.55 days, or 5.77 times 10 to the 6th seconds altogether, and finish Wednesday, the 16th of January, 2019 at 6 o'clock a.m. and 33 seconds. Well, that's the progress for today, and hopefully you understood the MRB constant. Write me. I get lonely not talking to people and not hearing back from people. I guess I'm talking to you, but I know people are watching these videos. I get the hits on YouTube, and I appreciate that. But I like people to respond to me and tell me they understand or they don't understand the MRB constant. And I make it clear. I can write you personally and make myself a little clearer, or give you some direction to find out for yourself a little more. So I'll try to make this. I have trouble making some of these public in YouTube, but I'm going to do my best to make. I'll eventually make it public, so you can put comments there. Or my address is bmmmburns@sbcglobal.net. Let me write that out for you. Let's see here. bmmm burns at sbcglobal.net. So there it is. I'll pause a second if you want to write it down, or you can pause the video. 1001. Okay, pause the video if you need more time to write it down. Please write me. And this is Marvin Burns signing off for now.